Dear students, now we are going to discuss a problem on convective mass transfers, especially in a mass transfer, convective mass transfer, the flow is the internal flow. So any flow, any fluid, that is a gas or liquid that may flow inside the tube along with some gases or some constituents. So how much amount of mass is transferred from gas to that wall surface, or other there is external flow, means that from outside gas to wall surface. Okay. Now we move to the problem. Listen, air at 25-degree atmospheric pressure containing a small quantities of iodine. So here the air that may be at 25 degrees Celsius uh, containing small quantities of iodine flows at the velocity of 5 meters per second inside a 3 centimeter diameter tube. So let us consider that is the diameter tube. Diameter of the tube is, say, that is called as a 3 centimeter. Then air along with small quantity of iodine. Air and iodine flows with the velocity of, say, that is called as a 5 meter per second at a temperature of air that is at 25 degrees Celsius. Calculate the mass transfer coefficient of air stream to the wall surface. How much amount of mass that may be deposited in the wall because of convective mass transfer? These are things we are going to find. So we are going to find there is a mass transfer coefficient H1. That is the we are going to find. Okay. Already we studied the conductive heat transfer problem. This is similar. This problem is more or less similar to the conductive heat transfer because this is a conductive mass transfer problems. So for this, first we are going to find uh, properties at the of the given condition of air. So at air uh, at 25 degrees Celsius, we have the properties. It's maybe that is 20 is given, then 30 is given. In between this, you are going to find the 25 degrees Celsius. Okay, so for the mass transfer problem, we need a kinematic viscosity. This is one is enough for finding the mass transfer coefficient. So we are going to find there is a kinematic viscosity. So this value, this table is taken from the data book. For our convenience, we should copy here. So 20 degrees Celsius, we have the kinematic viscosity which is equal to 15.06 into 10 to the power of minus 6. Then 30 degrees Celsius, we have a kinematic viscosity of 16 0 into 10 to the power of minus 6. The unit is, it is a meter square per second. This is also meter square per second. But we need a value that may be exactly around, that is a 25 degrees Celsius. We may calculate it with the help of interpolation method. So in interpolation method, there is x minus x1 divided by x2 minus x1 is equal to y minus y1 divided by y2 minus y1. So this is the taken, this is x1, this is x2, this is the value that is x, this is a y1, y2, what is the y you are going to find. So after substituting the values in the below equation, here x minus is equal to 25 minus 20 divided by 30 minus 20 is equal to y minus 15.06 into 10 to the power of minus 6 divided by 16 minus 15.06 into 10 to the power of minus 6. So by using the interpolation value, you may find the kinematic viscosity. It is a viscosity at 25 degrees Celsius, which may be approximately equal to 15.7 into 10 to the power of 6 meter square per second. So this property only, this is enough. So this is taken from the property of gases at 1 atmosphere pressure that is available in the that data book. Okay. I think this is available. So already we see the data book. So this is available in the page number. There is 33. In the 33, we are giving kinematic viscosity. So in between this 20 and 30, we may find the values. Okay. Then similarly, not similarly, we can also use the convective mass transfer correlations in the data book also. So in the convective mass transfer correlation, note that um, uh, this is in the available in the page number 174 in a mass transfer. So in a mass transfer, we are using a convective mass transfer. So in a convective mass transfer, this flow is nothing but that is the internal flow. So internal flow, laminar or turbulent, we doesn't know, but it is internal flow. So we may choose this particular area. So we also copy this content and paste it in the presentation for our convenience. Okay. Then okay. Then first, then again, after finding the properties, you are going to find the Reynolds number. Uh, Reynolds number. Whether the flow is laminar or turbulent. So we already we find the flow is internal. So internal, first one is internal flow. Then we can again move to the laminar or turbulent. Laminar turbulent, know the Reynolds number. Reynolds number is equal to u divided by u d divided by nu. So d is nothing but diameter. So u, then the problem it can be given as there is 5 meter per second. Diameter which is equal to 0.03 meter divided by kinetic viscosity is equal to 15.7 into 10 to the power of minus 6 meter square per second. So after substituting value, the Reynolds number is equal to 9550, approximately 9550. So which is greater than, that is a 2500. Therefore flow is turbulent. So this is similar to the problem what we solved in the convective heat transfer. Okay. Then after you finding the Reynolds number, you also find another one number that is called as a schemic number. So schemic number is similar to the Prandtl number available in the convective heat transfer. So schemic number that is given, there is a schemic number is equal to mu rho by d. So Sc is equal to, that is a mu, there is a rho into mu rho into d. Similarly, that is mu by rho, you already know that is equal to mu divided by d. So kinematic viscosity is 15.7 into 10 to the power of minus 6 meter square divided by second divided by d. What is d? D is nothing but many of you confuse that d is nothing but diameter. It is not a d, that is a DAB, that is a diffusion coefficient that is given in, that is a meter square per second. Okay, so this is a DAB. So for our convenience, we can be written as DAB. Somebody make a mistake in substituting DAB instead of diameter. So please be careful. This is a DAB, not a diameter. So there is a DAB. So DAB that is given in the problem. So it is equal to 2.50 into 10 to the power of 5, 10 to the power of minus 5. So 2.50 into 10 to the power of 5 meter square per second. So meter square per second means finally you can get the schemic number. The schemic number value is approximately 1.914. So this is second step over. So after substituting a schemic number, we are going to find what is called a Sherwood number. So this schemic number is more or less is similar to, that is a Prandtl number in convective heat transfer. So what the Prandtl number do in the convective mass transfer similar is the same as schemic number do in the mass transfer. Next one is Sherwood number. Sherwood number is similar to, that is a Nusselt number in convective heat transfer. So procedure is same for both the cases, but the dimension number is different for heat transfer and mass transfer. So here Sherwood number we are choosing. So here the internal flow is turbulent. This is Sherwood number. Then which is the value Reynolds number is 2000 to 35,000. We satisfy this condition because for our case the Reynolds number is 9500. So this condition is satisfied. Then schemic number for our case is that is 1.914. This condition also satisfied. So for both the condition is satisfied, we can take then Sherwood number is equal to 0.023 into Reynolds number of that is 0.83 into schemic number of 0.44. Okay. Then here what is a schemic number? So in a Nusselt number, convective heat transfer coefficient which is written as that is a HD divided by K. But in a Sherwood, here the Sherwood, no, it is not a schemic, that is a Sherwood number. This is called as Sherwood number. Sherwood number is H into D into D. So here Sherwood number that can be written as H. From this relation you can note that instead of X you are using a diameter. So H into diameter HD by K. Here also there is HD by K instead of DAB. Note that. So H is HM, which is convective mass transfer coefficient into diameter divided by diffusion coefficient, which is equal to 0.023 RE power 0.83 schemic number of 0.44. So we need only a mass transfer coefficient. So HM is equal to 0.023. Reynolds number you already find, so which is equal to 9550 whole power 0.83. Schemic number you find, so it is 1.914 into 0.44 into the DAB. There is a DAB divided by that is a diameter. So DAB value you know, that value is equal to 2.5 into 10 to the power of minus 6. Diameter you know the value which is equal to 0.3. So after substituting all the values, find you can get the mass transfer coefficient which is equal to 0.0119 meter per second. So this is the value you may get after the substitution. So this is a very simple problem which is similar to the convective heat transfer. Here using the Reynolds number is the same. So instead of Prandtl number you find the schemic number, instead of Nusselt number using the Sherwood number. So here in Nusselt number is just HD by K. Here also HD divided by instead of K we are using diffusion coefficient. Here the thermal conductivity is used, diffusion coefficient is